crane demolition. So we are going to do a little bit of technical stuff of types of cranes, what to think about if you're coming to demolish a crane, and then the main hazards or pitfalls that you could come across when carrying out that demolition work. So, and then we've got 4 different case studies. Some of them are a bit historical, some of them have been talked about before, but this is a nice place to put them all in together to give a good background on the subject and how we've managed some of the kind of hazards and difficult, challenging cranes that we've demolished in the past few years. So hopefully this is going to be good. So firstly, very basic types of crane that you could be asked to demolish or like come up for kind of tender for demolition. So gantry cranes, these could be both ones sat within a kind of pole frame shed. They could be standalone gantry cranes. We've got a good case study of one of those. Or they could be kind of stepped gantry cranes where the rails are on 2 different levels. So there's a lot of different types of gantry cranes, and even some container cranes, like ship-to-shore cranes, could be considered gantry cranes because containers run across the whole gantry. You get luffing jib cranes. So these are cranes where the jib is, well, luffs up and down. This is either by ropes or with a big luffing screw and a bit of a counterbalance, but these obviously, there's a bit of a mechanism involved, so you've got to consider how that jib's supported. Can it move? Or what is its range of motion? And can it kind of get down to touch the ground in its kind of operational state? Also, when it gets a bit more complicated, and these are a type of luffing crane, but you get kind of swan neck or jackknife jibs. So these are cranes with a bit of a mechanism. As the jib moves out to extend it over the radius, the jib kind of angles out and becomes flat. So it luffs, but there's a mechanism involved that allows the tip to go flat as it luffs. And finally, you get kind of flat top, or these can also be kind of A-frame cranes where the jib doesn't move up and down, it just slews round, and the radius is dealt with by kind of a travelling bogie system. So that's a basic overview of the types of cranes that you could get. Now, when it comes to demolish these, sometimes we have reasonable information, sometimes we don't have anything. So the main unknown on these cranes, apart from all the structural steel work, is ballast. So in some situations, it will be a known quantity. It could be concrete blocks, it could be big steel plates. Sometimes it is loose ballast, or it's just an unknown in a ballast container. Just some images of some of the cranes we've done recently with a variety of concrete blocks, rail tracks, just kind of poured concrete with bits of steel in it. It's quite an unknown, and this is where you get risk, because quantifying the volume and the weight of that ballast becomes a real challenge when you have limited access and you can't tell what it is. And then, how is your crane supported? So this is the other big thing that you need to think about. So the easiest and I guess most obvious is like an anchored crane. So this is your traditional kind of tower crane anchor. If you're got a crane on a construction site, and also some dock cranes, these will be anchored to a large concrete foundation, and that's cast in. You also get cranes on rail tracks, so they'll be on bogies. They can move along the rail, and therefore there is no positive connection between the crane and the ground because it moves along those rails. So the stability is provided purely by the self-weight of the crane and the ballast in it. You get gravity bases, where these are like rail cranes, but obviously not on a rail. They just sit onto the supports or onto the foundations, but there's no positive connection. So moving on, so demolition options. There's broadly five demolition options for these, and 2 of them are a bit similar. So the first one that we could look at, and this is only relevant obviously when you are looking at dock cranes, but you could bring in a large crane on a barge, and this is quite often how a lot of these cranes were constructed, and this would enable you to kind of lift the crane off from the water side, where you've got a better radius to lift off the kind of the jib sections that go over the water. So that's an example there. You get shore cranes, so any kind of crane that can be positioned on the dockside around the cranes or adjacent to it that can be used to lift the crane down sequentially. You could pull your crane down, so you could carry out pre-weakening of the crane and initiate a collapse. So we've got a case study on one of those that we've done there, and that can be applied to a lot of cranes, but obviously you need the space to do that safely. Mechanical demolition, so if the crane is quite small or if there's kind of the room to do it, and quite often for the lower sections of a crane, mechanical can be an option where you use large demolition spec excavators to get in and kind of take the crane apart. And finally, you could use explosives. So there's a number of examples online of where sufficient exclusion zones, you could use explosives to initiate a collapse and then deal with the crane once it's safely on the ground. So they are your main options for demolition, and each of those has their own hazards and challenges, and they're all viable in their own situations. So the hazards, so these are mainly related to dismantling piecemeal, but also applied to kind of mechanical and pull downs. So global instability, so what you're looking for there is the crane going to be globally unstable, so fall over at any point during your demolition sequence. So you're looking at the central gravity of your crane, the wind loading that it'd be subject to in that temporary condition. Is it free to slew or is it slew locked? So if the crane's free to slew, it will kind of slew into the direction in which the wind provides least resistance. Whereas if you've got to slew lock it to enable your demolition, then potentially you get higher wind loads onto the side of it that would need to be considered. Local instability in mechanisms. So a lot of these cranes will have been built in a sequence. The construction sequence of them has been lost through time and the drawings are not available to show how that is. So as you're dismantling it, you've got to check the stability of a number of members if you support to one end, and ensure that there's not going to be a lateral torsional buckling if you're removing supports and restraint. And also, a lot of cranes are mechanisms, so one end may initiate a collapse if you don't understand the mechanism in which the crane operates. So structural failure, fairly obvious, but as you dismantle it, you've got to make sure that the load path is maintained as close as possible to what it was during operation, and you're not overloading any elements of the crane during this process. So the most likely element is the slew ring of cranes, so making sure that the moment about the slew ring is within the kind of capacity of that and the operational capacity of that crane. Only relevant when you're dismantling cranes using other cranes, but you have to carry out weight estimates if the weights are unknown and you don't have drawings that outline it. So there's a potential for you overloading your lifting equipment or for the centers of gravity being inaccurate. So you need to allow for that. A lot of the lifts you undertake with these are dynamic lifts because of the situation in which you're doing it. So you need to have the appropriate factors of safety for a dynamic lift. So that is the basics of demolition and what you should be thinking about and considering. It's definitely not an exhaustive list, but it gives you a bit of a feel for what to be looking at and thinking about during the demolition. So we've got 4 case studies. There are a variety of different cranes, but hopefully it just gives you a feel for how we've managed those risks going through these. So first one is local to us up in Scotland. So we looked to dismantle 3 container cranes at Greenock Ocean Terminal. They were replaced to give the port more capacity. So the contractor doing it was Sam Evans and Sons, and the overall client for this was Peel Ports. So we carried out a survey, a weight takeoff, and a dismantling sequence for these cranes. We had very limited information. We had a single drawing that gave us the overall dimensions of that crane. But apart from that, we were very limited information-wise, so we needed to carry out a full survey of all the accessible elements to estimate the COG of those for dismantling it and kind of the stability of the crane that was to remain. So how we did that, we went up, we had a thickness gauge, we went and surveyed as much as we could, and we built a 3D model with information. So it was a fairly big crane, but at least we did it in good weather. And we built that 3D model. We could then use that to work out our centers of gravity of both the whole crane and the elements that we were lifting. And how we went about that. So initially, the crane was stuck with the jib up. The power was off, so we couldn't lower that jib easily to its horizontal position to lift it off. So we looked to remove some of the ballast in the form of the machine house, and then we started to dismantle the jib. So you can see the process there of, lift one was the machine house and equipment, and then we moved forward to taking off the jib into sections, and then the back span of the crane. And we looked at, how far that center of gravity moved at each of those stages compared to its operational state, and looked at the wind loading as well. From there on, we were just taking the crane top down. We were limited a bit by the capacity of the shore-based crane we were using, but that was the process of that, and we checked the stability. There was a situation on lift 5, it was, where we had to take out the cross beam at the back that kind of provided lateral restraint and braced them together, and that could have resulted in a lateral torsional instability of those beams. So we carried out the checks on that to make sure it was going to stay stable in that temporary condition, and then continued from there. That is Greenock Ocean Terminal. So we did 3 of these cranes. The first one was a 40-ton container crane, and the other 2 were 35 tons, but they had a different structural form, though similar, so we had to do unique assessments on all 3. Here's a video that Sam Evans made. Hopefully that's playing all right. Just gives you a bit of context. You can see the other 2 35-ton cranes in the background there that were still operational at this point while we were taking down the 40-tonner. That's the top section of jib coming off, and then the main section. And then from there, it's the kind of back spans and the ties. And overall, this was, a successful project. I think the only thing that hindered it was the weather on the west coast, which was understandably not great. So, second project we're going to talk about, and you'll see why I don't have too many pictures for this one, was some tower cranes or static tower cranes at Devonport Docks. So Devonport Docks is obviously a military base, so we were limited in the images we could take and that we could share. But Google Maps gives us an idea of what we were taking out. So we looked at crane 2049, which is that left-hand one labelled up there, and 2048 there. There was also another couple of cranes around the site, which were a bit smaller, that we aided in the dismantling of. So we did this job for Technical Demolition Services. And again, we carried out surveys, weight takeoffs, and dismantling sequences for the cranes. Some of these cranes we had reasonable drawings for, so it's more of a desk study. Some of the cranes we had to go on site and do the survey for. So I'll start off talking about 2049, which is the left-hand crane there. It's kind of an A-framed flat-top crane with kind of a cable-stayed jib. So we had 2 really useful drawings that gave the weights of the individual elements of the cranes and their centers of gravity. You can see them both there. The second drawing gave a good kind of overview of the stability mechanism of the crane and the wind loads it had been designed for. And that was really useful for us to look at how the crane would kind of take the wind loads, because we were having to slew lock it over the quayside to ensure we had the correct radius for our crane to dismantle it. And we were limited by the size of the crane we could use on those docks and the positions we could put it in. So we had to look at quite a small piecemeal demolition sequence. So as you can see there, left-hand drawing shows a bit about where we were looking to slew the crane to and lock it, and then how we were going to do that dismantling sequence. So again, we looked at taking some of the counterweight out of the back span and then dismantling the jib in a sequential fashion, taking a section of the jib and the tie out in each one. And we worked it back to the main tower and then from there, it was a fairly simple case of dismantling the crane top down. We had to put some quite stringent restrictions on the wind because the crane was designed to slew either into or out of the wind, and at one point, due to the removal of all the machine house and things, that would alter. It would switch round because the area to the left of the tower would be greater than the area to the right, etc. So we just had to look at that, look at how that would affect the stability, and just carry out the checks to satisfy ourselves that it would be stable. 2049, which was the next crane over, was a slightly different structure. It was another A-frame, flat-topped crane, but only had a single stay on it. We didn't have any drawings for this one, so we carried out a full kind of survey of the crane and calculated the weights from that. Yeah, again, taking some of the ballast off, taking bits of the jib off, and then the complicated bit was the removal of that main jib section and the cable stay. There were some documents, though they weren't drawings, that estimated that the jib weighed somewhere between 10 and 20 tons, and because we weren't sure of that, we had to carry out a partial lift of it to confirm the weight prior to cutting it free, so it was a returnable lift at that point when we were checking the weights, and that kind of confirmed what we were doing prior to cutting it away. Once we'd taken the jib off, the back span came off, and yeah, it went top down to the base. So this brings us on to the A&P Tyne 40-ton crane.
Thank you, David. Morning, everyone. So yeah, A&P Tyne 40-ton dock crane. This is a job that we conducted on behalf of Sam Evans and Sons, and it was the crane was located in Newcastle upon Tyne at the A&P Tyne site. So this is a swan neck crane. They've talked about those previously, and this luffs by use of a luffing screw, which is aided by a counterweight at the back of the crane and helps the jib basically retract and extend. So what do we need to do when we get a package like this in? We need to review the information that's provided to us by the client. In this case, we received some information, but not enough that we felt we could continue with the design of the dismantling sequence for the crane. So then we took a trip down to Newcastle upon Tyne to survey the cranes, where we needed to gather all the information required at that point, which would then go on to inform our stability assessment and the dismantling sequence. Both the stability assessment and dismantling sequence, they go in tandem. You need one to be able to conduct the other. So yeah, it's important that we do them at the same time. So here's a bit of a walk around of the crane from when we were on site on that day. So just to give you a bit of an overview of some of the elements of the crane. So the top left picture is within the cap girder. So that's the slew ring. So the revolving portion of the crane at the top, that is the mechanism that aids the slewing of the crane, revolves it around basically. And the image below that is some of the hoist gear within the machine house. And moving over to our right, we can see the long travel gear at the bottom. So this crane was operated on rails and moved up and down the quay side using rail tracks. And then moving on to our right again, we see the luffing screw that was talked about previously. So a big piece of threaded bar, and that is driven by a motor within the A-frame, basically pushing the jib in and out. That's aided by a counterweight on the back, which takes some of that load off that luffing screw and the motor, and yeah, to move the jib in and out. And then a nice photo from the underneath of the crane. We can see the platform, which the main mast is sat on. There's a big pin in there, and then the lattice mast goes up and then into the cap girder and the slew ring at the top, and then the revolving portion of the crane is above that. The whole mast revolves within that pinned connection within the platform. Yeah. So when we were on site, we had a look around the crane, we chatted to some of the operatives on site, and then we discovered that this crane had actually travelled with one of the operators to multiple locations along the Tyne and different quay sides, and the gentleman had a filofax full of lots of documentation. So we had a bit of a rummage through there and we came across this drawing. So this is a stability diagram similar to the ones that David showed previously, different cranes. So it gives us all of the weights of the individual component as well as the lever arms for the components with respect to the datum on that drawing. And this is gold for us as temporary works engineers, as we didn't have a drawing like this. As David mentioned, we had to conduct a full survey of the crane, record all the thicknesses and the sizes of all of the structural members, and basically draw a big 3D model and produce a weight takeoff for the crane. So the two boxes that I'd circled on the previous slide, this is just basically those tables blown up. So when we're looking at this crane, we need to think about the global stability of the crane, as well as like local instability of the crane as well. So there's two elements that we're thinking about here. Local instability of the crane, so any element that we're cutting off, but most importantly here is the moment within that slew ring. So as the crane operates, transmitting that load from the lift back into the slewing mechanism within the cap girder, we need to make sure that at all times that the moment within that slew ring stays within the operational range of the slew ring. So the table on the left here is no load at minimum radius. This is dead weights of the revolving portion above the slew ring. Gives us the weights and also the lever arm of each of those components, and then which then in turn gives us the moment within the slew ring. That's for no load at minimum radius. There's also a table for 1.75 times full load at max radius, which gives us a higher imposed moment onto the slew ring. The second portion of this is looking at global stability. So looking at the table on the right hand side, we need to determine, before thinking about taking the crane down, what our operational range of center of masses of the crane. And loading, we need to think about, no load minimum radius with wind on the front of the crane, which is then going to push that center of gravity backwards. Here we can see on the table that no load at min radius with wind on the front of the crane pushes the center of gravity of the crane 13.1 feet backwards. We then also need to look in the opposite direction, and we need to look at 1.75 times the full load at max radius, so 135 feet, with wind on the back of the crane, and then that gives us our operational constraint forwards. That's 15 feet forwards. So at all times through conducting the stability assessment and the dismantling sequence, we need to make sure that we keep the crane within those limits as it's coming down. So onto the drawing part and the stability, the dismantling sequence. So we want to set this crane up in a way that we can take it down effectively. Thankfully, this crane was in operation still, and we could move the jib all the way up to the minimum radius position. This meant that we could also bring the center of gravity as close to the center line of the crane as possible before we started the dismantling sequence. And we need to set the crane up in a way so we remove all of the additional components that aren't required structurally during the dismantling of the crane. So we remove the hook blocks and any of the winch gear and all of that sort of stuff. The ballast arm on the back, that was there to aid the luffing screw, as I'd previously said. We chocked this against the A-frame because the whole jib was dependent on each of the components. As you'll see later in the sequence, this part of the counterweight would have been free to rotate, so we chocked it against the A-frame to ensure that it wasn't going to rotate once we started cutting the jib apart. Moving on to the right, we then removed the ballast and conducted a stability assessment at that point, looking at the moment within the slew ring and the center of gravity of the full crane. And we see that it's moved forwards 296 millimeters, so that was acceptable. So then we moved on to the next stage. So then we looked at taking the front cantilevering section of the jib off. We then, basically indicated the lift weight to the client. We indicated that it was a non-returnable lift because as this is cut, there's no way for the crane to put that back down again. And we specified that they cut the jib free below the final bay of the cantilever, so you're not impacting that structural connection between the jib, front jib and the cantilever. We did the stability assessment again, and the COG then moved backwards 115 mil. So this was a bit of an interesting part of the crane. So we knew at this stage that whichever part of the main jib we cut, one part of it was going to rotate as it was structurally dependent on all of the other elements it was connected to. So the way we sequenced this was we specified that the crane was to hold the top of the main ties, so the red portion to the left-hand side of the screen there. The final bay of the cantilever was cut at the node point to the main jib. This would allow the cantilever to rotate in towards the main ties. The crane would then rotate the main ties into the two vertical, and the main ties were cut at the top of the A-frame and lifted out of position. Again, we conducted the stability assessment on this, and the COG moved 204 mil backwards from the centre line of the crane. The main jib, so again, we indicated the lift weights and that this was a non-returnable lift, and we sequenced it in a way that we cut the base of the jib free, so that the luffing screw was stopping the jib from swinging out of the crane, and then the final cut was conducted and the luffing screw was cut and the jib was lifted out of position. We can see the lift being conducted down on the right hand side. And then moving on to the ballast arm and the counterweight. So this was chocked in the first stage, as I previously mentioned. The mobile crane that was used to dismantle this then slung the ballast arm at the top of the A-frame. Connection to the top of the A-frame is cut, again, rotated to vertical and then lifted out of place. The stability of this was assessed, and it moved the COG 71 mil backwards from the centre line. Yeah, non-returnable lift again, and a lift weight of 19 tons. So. At this point, the stability of the crane was ensured. We'd moved all of the structural components, imposing a moment or a significant moment on the crane, and we were left with the A-frame. And from this point, it was top down. A demo of the structure, so we cut the A-frame at the top of the machine house and lifted that out of position. See on the right there. And then just some photos of the rest of the sequence, so going top down. So super base, machine house and cab was lifted off in one and cut at the top of the mast and lifted out of position. And then the central mast, which was supported with inside the cap girder and the platform at the bottom, that was cut a couple of bays up from the platform, so that the crane had the reach to pull full mast out of the cap girder, and then that was lifted out with the crane. And then the tower slung by the crane around the cap girder, the legs were cut at the top of the platform, that was lifted out, and the main platform on the right hand side, as you can see, cut at the top of the long travel gear and lifted out of position. And then it's a mechanical demo of the long travel gear, and from there on, I'm going to hand back to David.
Thank you very much. So now the final case study I'm going to talk about is a bit of a historical one. So I'm going to talk about the Willesden gantry crane demolition that was done back in either 2018 or 2019. It was the project, well, one of the projects that I put forward for my chartership review. So it was a while ago. So the contractor for this was John F. Hunt, and it was, the overall client was HS2. So this was to free up space at Willesden Yard, which was then used as, I think, a storage area for a lot of the tunnelling works that were done for HS2 and to aid in the Old Oak Common station development. So there were 3 gantry cranes that were removed. Gantry crane B, which is shown in the picture, was one type, and then gantry crane, I think, C and D were a slightly different type, and they were removed in a different way. So the site you can see here, so you've got gantry crane B that is closest to the network rail boundary, and there were live trains obviously on the other side of that boundary, and then you've got C and D, which are a bit further away and were a different kind of form of gantry crane that we used for kind of moving containers from trains onto trucks and away. So that gives you a bit of context on the site. So gantry crane C and D, how we managed these was they were dismantled with a large mobile crane. We lifted the main turntable off, and then we dismantled the rest of the crane, kind of piecemeal cutting it into sections with the crane supporting the self weight. You can see there where the cranes were and the kind of the crane position that we used. It was a fairly big crane. It was a 550-ton mobile crane with a super lift on it, which had some pretty significant outrigger loads we needed to consider. And some sketches here of what the work we did to check the outrigger loads into the ground, and looking at the kind of the unit that was to be lifted off and removed. So you can see here where the picture of the crane. So we pulled the turntable off there, which is that central section, and then the remaining section was lifted, and we've got a little video that shows how this process was done. It was lifted and the legs were progressively cut down, and that's how we kind of safely dismantled it. So hopefully this will work. So you can see gantry crane B is still there in the background at this point. You can see this was crane D, and then the crane was de-rigged after these works and moved over, and the other crane was done in exactly the same fashion. You can see the rigging up the mobile crane here, which takes up most of the video. Turntable taken off. And the main frame was picked up and then progressively cut at ground level to minimize the working at height, and then mechanically demolished following this. And then the crane was de-rigged and moved over to the next site. So gantry crane B, this was the more interesting crane as far as we were concerned. So this was directly adjacent to the network rail lines, which limited a bit on what we could do. But the proposal was to pull this crane over and then demolish it at ground level. So to enable that to happen, we needed to move the crane from where it was positioned to a place that was safer to carry out this pull down, because there's a potential, if the pull down did not go as planned, that it would cross the network rail boundary. So I think during a Christmas possession, the crane was moved using SPMTs. We designed a temporary hard standing that sat above the rail lines, but still allowed trains to pass because there were trains coming in on a weekly basis. And then we could take that crane, rotate it through 90 degrees so that the pull direction was parallel to the boundary, and position it further away from the boundary to keep that safe. So this is a drawing that shows the proposed pull down sequence. So we were to create hinges at the top of the legs, and that would initiate or create a mechanism with a pull force that would allow the crane to collapse. We used some piles of loose fill to dissipate any of the vibration from the collapse and kind of minimize the effect on the adjacent assets. And it kind of shows the proposed collapse sequence there, and what we were planning to do and how we were going to pull it. So the pre-weakening. So we carried out we carried out a survey of the crane to assess the wind loading onto it and to assess the self weight. We looked at the thickness of the legs that we were proposing to cut, and then we calculated how much of those legs we could safely cut while maintaining the stability in the short term, but cutting enough to ensure that we could pull the crane over. So how we did this was those drawings there. You can see we've left the back web of this box section in place, which is indicated blue, it's not cut, and then we'd shimmed the front section and left some tabs in place. That provided enough compressive capacity to keep the crane upright and support the self weight, and enough moment capacity to resist the wind loads in the temporary condition, with some pretty strict limits on the wind loads or the wind speeds that we could accommodate during this process, so we needed a clear weather window to carry out this demolition and initiate the pull down. So the final cuts were made the morning before the pull down, so there was a limited time in which the crane was in this final state. We also ensured that the cuts were made in a sequence that meant the final cuts were done with the burner in a position of safety outside of the full radius of the crane. We were a bit unsure on the internal structure, so we had one of the first cuts we made was some big windows into the box section to check for the internal diaphragms and stiffeners. In the end, there weren't any diaphragms. There were some angles running up the inside that formed the bracing. But because we did that as a first stage, we could then allow for that in the sequence of works, and we cut them out prior to continuing with the rest of the demolition. So that was the pre-weakening work. You can kind of see in that top picture there, you can see the box cut out where we checked and the cuts done on those front legs, with the final cuts being done on the back legs at this stage. We'd rigged up the crane already to an excavator to provide the pull force. This is the final video, which kind of shows the pull down of the crane. So you can see the rigging going tight as the excavator drives away, and the kind of destabilizing force was applied, and the rigging goes slack as the collapse was initiated. And the crane was safely on the floor and kind of could be mechanically demolished safely. So that brings us to the end of our presentation.